Good morning. So today we are going to learn about geodesy. What is geodesy? Let's define what is geodesy. Okay. So in the process of this learning this chapter, we will able to apply an elementary understanding of the way the Earth's gravity field affects surveying observation and how these observation can be reduced from earth's topography to map. Okay, so it how it can be put on to a map projections where we have observed on the land features. Like for example, when we take mountains, when we want to project mountains, it is very uneven in surface. Okay, so these uneven surfaces, when we want to project it, how we can do it. So in this learning system, we will understand how we can appropriately project all these features of the earth on a proper topographical map. Now implement we will learn to implement foundational knowledge of geometry of elliptoid and map of projection. uh, we will learn to incorporate the geocentric datum and map grid principle into geodetic surveying. The practice on establishing geodetic datum and transforming position of from datum to datum. All right. So in this lesson plan, we will learn that. So then we have geodetic system. Geodetic system is the mathematical presentation of Earth. It is used in geodesy, navigation, surveying. Okay, it is used in geodesy, navigation, and surveying. So a datum is a set of values used to define a specific geodetic system. Okay, so geodesy is a way of defining how we are specifically the geoid system is there. All right, like north pole, south pole, equator, they all may be assumed to be a different position on a different datum. So every datum, each style, if technique of datum will have a different different positioning of these north pole, the south poles, the equator, or any land feature. Okay, so I will tell you. So the true point may be varying a slightly different from a different geodetic systems that can be followed. So there are local geodetic systems, there are some universally or internationally accepted geodetic system to for a map projections. Okay, so different datum use different estimates of practices, precise shape of the earth and precise size of the earth. Okay, they are called as a reference elliptoid. So what is it? The different datum used to estimate the precise size and shape of the earth is called as a reference elliptoid. Or you can say in another way, you are making taking out an average approximate shape of the earth. Now horizontal datum is used to describe a point on the earth's surface. For example, latitude and longitude. So latitude and longitude is a example of horizontal datum. And vertical datum is used to measure height or the depth. So height in case of when you are going to measure Mount Everest, and depth when you are going to measure depth of the ocean, the abysses, the ocean floor. So that is the underwater depth. Now, in the geodetic system or the Earth elliptoid, surveying is the art of making measurements of relative position of natural and man-made features on the Earth's surface. And the presentation of this information either is in geographical or numerical in nature. Okay, so it is basically graphical presentation or numerical presentation. Now geodesy is the discipline that deals with the measurement and representation of the earth, including its gravity field in three dimension, time varying spaces, in three dimension time varying spaces. So geodesy focuses on the earth and neglects any man-made feature on it. For example, buildings and public utility places are basically ignored when you are taking up a geodesy. So there can be, skyscrapers which is quite a significant height, but it will not be included in the process, or way of geodesy. So while surveying use the result of geodesy for the positioning and mapping of these features. So these positioning and mapping of the features like mountains, where is your Mount Everest is located, where is Chota Nagpur plateau is located, where is Kashmir Valley located. These are the position geospatial positionings. So these geospatial positioning is done with the help of geodesy. Okay. Now, the geoid. What is geoid? This is defined as the equipotential surface that most closely correspond to the mean sea level. So, geoid is an equipotential surface that is mostly close to the mean sea level. When you take the mean sea level and you try to shape the earth based on it. Okay, so there can be areas where it is a depression, where there is a land feature which is going below the mean sea level, but it will go along that path only. So it will try to make a more smoother pattern. So in an elliptoid may not be sufficiently accurate for detailed measurement at a large scale, but the earth's surface is slightly, because it is very irregular in shape, so it is in a more of a shape of a pear, where somewhere with a bump and hollows in it. So these bumps and hollows are also considered in the geodetic measurement system. Now geoid is used in this it is a model of gravity data. We can see the surface or measure it directly. The geoid surface is irregular, and unlike the reference elliptoid, which is a mathematical idealized representation of physical Earth, but considerably a smoother than the Earth's physical surfaces. Although the physical Earth has a excursion of about uh, 8,000 meters, that could be more of Mount Everest height. It is more than 8,000 meter, and depth of a Dead Sea or an ocean floor that can be minus 400 meters or 418 meters. So the geoid varying range from minus 106 to plus 85 meter. So less than 200 meter compared to the perfect geometrical elliptoid. So it is less than 200 meter less than the perfect geometrical elliptoid. Now, a reference elliptoid. What is a reference elliptoid? Let's try to understand that. A reference elliptoid is a mathematically defined surface that approximate the geoid, the true figure of the earth, which is the true figure of the earth. So it is a reference elliptoid is a mathematically defined surface that approximate the geoid. The true figure, geoid is the true figure of the earth, which is, I will show you here. It is here. This one, if you see, this is a reference circle, this orange line, and geoid, which we mean is, this is the general mean sea level shape that we are taking of the earth, and the actual shape of the earth is represented here in the blue. So actual, so it is basically, the geoid is basically taking out the average of perfect elliptoid and the proper earth surfaces. Okay. So now what is happening here, some of the most popular reference elliptoids are, number one, it was the earliest attempt of giving a shape to the earth, that is Clark in 1866, then in International 1924, and then came WGS 1984. Okay, so currently the most common reference elliptoid used and that use is in context of GPS or global positioning system is WGS 84. In other way, WGS 1984. Okay, so it is the most widely and currently used way of referencing the Earth shape for the use of global positioning system. All right. Now, many elliptoid has been defined in the world. Uh, you know, some are like locally elliptoid and have been establishing to fit the geoid, that is the mean sea level, well over an area of a local interest. So, which is in past were never a large, never more larger than the continent itself. So there will be a technique originating at Asia will have a different geodetic pattern or measurement, whereas similar activity going on in America will have a different, because they are representing that part of the geoid. So each increased demand of global surveying, so it is with the increasing demand of global surveying, work is under to develop global reference elliptoid in context to local elliptoid, which applies only to a specific country or localized area of the earth surfaces. Okay, now global elliptoid approximate the geoid as a mean of earth's elliptoids. Now international union of geodesy and geophysics plays a central role in establishing these reference figures. Okay, so basically International Union of Geodesy and Geophysics has the role in playing the central authority to establish this reference figures. Okay, now let's understand the basics of geodesy. Geo means earth and desi means the study. So basically, it means the study of the earth. All right. So geodesy is the science of measurement and mapping of the earth's surfaces. Okay, so, like Merriam-Webster has explained, it is a branch of applied mathematics concerned with determination of size and shape of the Earth and exact position of point on on its surface with a description of variation of its gravity field. So, gravitational field can be different. So, what is the variation of this gravity field? That is also in context of geodesy. All right. So let's try to understand various types of geodesy. One is geometrical geodesy, the other one is physical geodesy, and satellite based geodesy. Geometrical geodesy is concerned with describing locations in terms of geometry. Okay. Now, consequently, coordinate systems are one of the primary product of geometrical geodesy. Coordinate system means longitudes and latitudes. The combinations of longitude and latitudes are called coordinates. So physical geodesy is concerned with determining the earth's gravity field, which is necessary for establishing height. Okay, now satellite geodesy is concerned with using orbiting satellite to obtain data and geodic for geodic purposes. Okay, now, a spherical model of an Earth. This is a spherical model of an Earth trying to explain that how what is the radius of the Earth, where you find the feature and the diameter of the Earth, and it is how it is calculated. So first, the spherical model of the Earth was tried out to be explained by a famous Greek philosopher known as Eratosthenes. Eratosthenes has observed that on the day of the summer solstice, that is between 20 to 22 of June, it is the one of these are the days when days are the longest in the year. So 21st June is the day when the day is the longest. Okay, so this, and by the midday the sun had shone on the features. So one day he observed that the sunshine is directly on the well. So that he saw the reflection. One reflection had a slightly oblique, whereas on the when he would travel to another place on the same day, around the same days, he had seen the reflection of the sun had a different angle. So when he studied this different angle, he understood that first he saw a reflection of sun on serene, where he found that the sun is directly shining in the center of the well. Okay, when he went back to Alexandria, and again and around the same time he had seen that in Alexandria the sunshine is slightly slanted. Okay, then with this help of change in the angulation, like that is Alexandria is being far away from about 500 miles from Cyrene. He had calculated the approximate variation that is coming. So he knew that at the same time the sun was not directly overhead at Alexandria. Instead it is casted a shadow which is vertical to 1/5 of the circle. Okay, so 1/50th of the circle, that means it had about 7 degree 12 minute deviations. So he knew that Alexandria and Cyrene was about 500 miles apart. To this observation, Eratosthenes concluded that the circumference of the Earth was to be 50 into 500 miles, which comes out to be 25,000 miles of a circumference. So the circumference of the Earth he calculated by seeing the angulation of the sun which was falling on the, and that's how he had calculated that this would have been the approximate circumference of the Earth. All right. So spherical model of the Earth, this accepted the value along the equator. That is, most accepted value is 24,900 miles. But if you measure the Earth through the poles, it is like through the poles along the like this elliptical, slanting, it will go about 24,860 miles. That means there is a 1% of variation within the 1% of today's accepted circumferences. So Eratosthenes concluded we are highly regarded at that time, and his estimation of the Earth size was accepted for hundreds of years forward. And this acceptance of the Earth's shape was had helped many geographers and cartographers to represent a particular feature, almost trying to accurately whether towards the direction, in context of direction or in context of shape of the place. Now, how do we define the shape of the Earth? We think the Earth is sphere. It is not sphere. Okay, it is actually a spheroid. So slightly larger in radius, and at the equator and at the poles. Okay. So then we have elliptoid. An elliptoid is a mathematical figure which is defined by the semi-major axis and semi-minor axis. Semi-major axis is, this is the semi-major axis coming from the center to here, and semi-minor axis is like from center to the towards the pole. Okay, and also considering, because Earth is not smooth in just like the circle which is shown here, it has somewhere depression, somewhere elevation. So that flattening or uprising of the feature will be included in it. Okay, so it is simply a geometrical surface and cannot be sensed by the instrument. So it cannot be instrumentalized, used in the instruments. So it cannot be instrumentalized. Now elliptoid or a spheroid, now rotation of the ellipses around the axis is like this. Suppose Earth is moving from west to east, right? Earth is moving from west to east, right? That's why we see the sun rising from the east, right? Now when it is moving west to east, what is happening here? This is the minor axis, this is the major axis, and this one, third one, is giving you a third dimension of its rotation. Okay, the selection of this spheroid is what determines the size of the earth. Okay, now what determines the size of the earth? It is determined by the semi minor axis at the polar radius. Okay, and semi major axis at the equatorial radius. So each, by the way of WGS 84 value, is almost how much, 64, almost 64 thousand meters, and here also 60 over 64,000 meters. Okay, so these are the elliptoidal parameters. Okay, now real earth, how, what is the real earth? Real earth is how it is shaped like this. It is more of a shape of a pear. It is neither an orange, neither like a ball. It is more like a shape of a pear. Okay, so an elliptoid earth model is no longer tangible, that it is accurate. Okay, so the deviation of physical measurement of the referred from the elliptoid model can no longer be ignored. So the geoid anomaly is the difference between the geoid surface and the reference elliptoid. Okay, now elliptoid, the differences between the elliptoid and the geoid. Simply, it is mathematical definition and described by the two parameters and cannot be sensed by the instruments. Okay, now geoid is what? Geoid is a complicated physical in definition, and has description by infinite number of parameters, and can be sensed by the instruments. Okay, uh, let's go further. Elliptoid and geoid is like this. So this is a elliptoid surface. This pink line shows the geoid surface, and this brown line is representing the actual surface of the earth. So it is more like a stone. If you see a round shape of a stone, it has a lot of what do you call, even surfaces. That's what the shape of the earth is. Okay, since the geoid varies due to the local anomaly, we must have a approximate with the elliptoid. Okay, so this is the difference between geoid, elliptoid, and the actual surface of the earth. So this is an elliptoid trying to reference the earth, where you are leaving out the shape of the American continent, the southern continent, and only North America is like closely be represented by the this elliptoid technique. Okay, now here this is the third circle. This is the geoid circle. Earlier the red circle showing the elliptoid, which is well representing the North America, but there is a deviation in representation of European continent. America, Africa is nowhere close to it. Okay, somewhere close to European continent also it is representing an North American continent, but in the southern hemisphere it is not properly representing. When we come into spheroid shape or geoid shape, this is not representing anything at all. It is all of these presentation of the earth will be exaggerated. So we have to choose the optimum mean of representing the earth. Okay, now, elliptoid and geoid, unfortunately, the density of the Earth crust is not uniform, and there are many heavy rocks, like iron ore deposits, which have a stronger attraction than the lighter materials. Therefore, the geoid, which is a gravitational field, uh, will not be simply projected in a mathematical surfaces. Okay, so similarly, when we have a physical feature growing on the earth, you will have that it will, as it moves further away from the surface, the geoid surface, it will have a little bit of deviation from the you know actual gravitational pull. All right. So what it will start curving towards the other end. Okay. Now, orthometric heights. Now, let's understand what is orthometric heights. The perpendicular vertical distance between the geoid and the land surfaces. So, that is orthometric height. Then we have height difference between the elliptoid and geoid is called a undulation. Now, the obtained orthometric height, the geoid undulation must be accounted for. So, to obtain orthometric height, we need to account for geoid undulation. Uh, okay, so we need to keep that thing into mind. Now, latitude and longitude. So, what is latitude? Latitude is the parallels, and longitude is the meridians. So, the prime meridian is the 0 degree meridian, which passes through Greenwich, and equator is latitudinal or parallel meridians, and equator is the 0 degree parallel meridian. All right. Then we have a length on meridians and parallels. So each meridian and parallels have a different length from when you take it from the center of the globe. So we have done this thing in our projection, in our cartography. So I will not cover it again. So you must be knowing it, all together. So what is coordinate system? It is the basically the grid, and what are the various axes, the x-axis, the y-axis. All right. So any set of numbers usually set on a that has to be set on 2 or 3 dimensions, used to determine the location relative to other location in 2 or 3 dimensions is what we need to take a assistance of grid system. Now, global cardinal coordinates are based on x and y axis and z axis. Um, a system for the whole earth, that is non-manageable, and it is difficult to relate to other location when translated in 2 dimensions. So the coordinate is defined as the geometrical presentation. So the y-axis shows you the latitude, the z-axis show you the longitude, and the x-axis shows you the directions, the intersection of these latitudes and the longitudes. Now, geographic coordinates. We also know what is the geographic coordinates. Latitudes and longitudes defined using the elliptoids, and an ellipsis rotates around its axis. The evolution, the elevation from, that is the the 3D direction, is defined is as z, using the geoid as a surface of a constant gravitational potential. Okay. The origin of the geographic coordinate system is a combination of latitudes and longitudes. Okay. Now the planar coordinate system is defined by a pair of orthogonal uh, axes drawn through a origin. Okay. Now, geodesy, let's understand again, comprehending the entire thing. Geodesy is the science that determines the Earth's size and shape. Elliptoid is the mathematical surface which approximates the Earth's shape and size. It is approximate. It is a technique of approximation. Then datum is the mathematical model developed to fit the physical surface of the Earth, and coordinates is the value that relates a point to a mathematical defined surface. Okay. So the common datum which we use are North American datum, that 1927, that is also called as NAD 27. NAD 27 use the Clark 1866 spheroid technique. Reference point is located at the Medias range of Kansas. Okay, and based on the ground survey information in the year 1800s. So then we have North American datum of 1983, that is NAD 83. It used GRS 80, that is geodic reference system of a spheroid using the Earth Earth center as a reference point. So they are taking the reference point, means the focus point as the Earth center. Whereas in the NAD 27, Kansas was the reference point, whereas NAD 23, Earth center, the core is the reference point rather than the surface. Okay, so based on the ground survey and satellite information, it was developed. Then we come to the latest, most widely used datum system, which is WGS 1984, or we can also call it WGS 84, the most recently developed datum framework for measurement of uh, for a wider range. Now, the Earth-centered or geocentric positive. So, this Earth is a centered or a geocentric positive, system. Now, it was developed by the U.S. military for the purpose of GPS system used for as WGS 84. It was developed during the time of Cold War, when there was a race between the two superpowers of the earth, that is Russia, sorry, the former USSR and USA. So this former USSR and USA, immediately after the world wars, went into Cold War situation, which existed for late early 90s, and after the disintegration of USSR, the Cold War finished off. But during this period, there was many space oriented uh, efforts were done. Among that, this WGS 84 was one of the key achievement of the US military operations to reach the space, then also to launch the satellites into the space, so that they have this positioning. Or so when you want to get your what do you call spacecraft back into the earth, you need to have a positioning system. To establish the positioning system, this GPS system was developed. WGS 84 was it was implemented and applied in this technique. Okay, so overall, and concluding this um, what do you call lesson, let's understand that is an earth centered system, that is the earth fixed terrestrial reference system or geodetic datum. WGS 84 is based on a constant set of constant and model parameters that are described the earth's shape and size and the gravity and geomagnetic field. Okay, so WGS 84 is standardized US Department Defense definition of global reference system for geospatial information. So for a geospatial information, it was developed by the US Department of the Defense. Now, global geodetic system, that is in 1984, spheroid explains, which is more or less identical to the mathematical reference to the geodetic reference system developed in 1980, that is GRS 80. It is close to that. Okay, now compatible with the international terrestrial reference system. Also, it is also compatible by the ITRS system. The National Geospatial Intelligence Agency is responsible for organizing for WGS 84. Now, WGS 84 is a reference system of global positioning system, the GPS that we are using in today's time. So, concluding this, geodesy involves the measurement and monitoring of the size and the shape of the Earth, including the gravitational field, in a three-dimension time varying space. It includes topics such as global positioning system, airborne or terrestrial lidar, gravity, Earth mass distribution, plate motion, sea level rise, soil moisture, snowfall, and varied dimensions. Even it also explains the isostasy, fault terrain, and all these dimensions are covered in a technology advance in geodesy and advancing the way we make measurements and observation, leading to a better understanding of the Earth processes. It integrates the integrating geodesy into the understanding of the aids uh, of student understanding, you guys understanding the process of science. It includes how measurements are made and can teach a valuable skills in using the cutting edge instruments and tools and data sets like GIS platform. Okay, so overall, uh, uh, G- uh, Geodesy or Datum system helps us in our modern navigation pattern, like whether it is aviation, or it is navigation in this ocean, or you are finding a Uber cab. Everywhere you are using this datum system. Okay, so I hope all of you have understood it. Any questions, you can ask me any questions, and we will continue with the next topic tomorrow. Meanwhile, please go to the LMS and take your quiz. Okay, so there are certain quiz given in your LMS. Go to the LMS and take your quiz.